Hello everyone and welcome to this presentation. I'm Minh Nguyen from University of Klagenfurt, and today I would like to present our paper Scalable High Efficiency Video Coding Based HTTP Adaptive Streaming over QUIC. Our presentation will start with motivation and contributions. After that, I will describe our proposed method and give some evaluation and discussion. Finally, the presentation ended by conclusion and future work. About our motivation, well, in terms of protocols, HTTP2 still suffers from head-of-line blocking. Meanwhile, QUIC running on top of UDP can tackle this issue. Therefore, we would like to evaluate how QUIC can support adaptive video streaming when there's packet loss. Regarding video streaming, adaptive bitrate algorithms are mainly designed for either non-scalable or scalable video coding formats, so there's a lack of an approach that works well for both non-scalable and scalable video coding. It should be noted that in non-scalable video, the client downloads one file to achieve a particular quality. Meanwhile, for scalable video streaming, the client needs to download one or multiple layers. For example, in the left bottom figure, we see that for non-scalable video, the client would like to download one file to achieve the HD quality. However, for scalable video, to have an HD quality, the client needs to download one base layer and one enhancement layer. These features of scalable video can reduce content redundancy, and because the enhancement layers are downloaded separately, the client can adapt faster to the fluctuation of the bandwidth. The contributions of this paper are twofold. First, we provide a systematic comparison of QUIC and HTTP2 regarding the multiplexing features with and without packet loss. Second, we propose a non-scalable video streaming APR algorithm in combination with an additional download technique to improve the video quality and provide a smooth adaptation behavior. Before going to the proposed method, I will briefly introduce some APR algorithms which will be used in our paper. The first one is an aggressive APR denoted by IgG. It aggressively selects the maximum bitrate that is lower than the estimated throughput for the next segment. The second one is a scalable-based method called backfilling. It is illustrated in the top figure. The order of the downloaded layers is from layer 1 to 5, which are base layers of 5 segments, until the buffer is full. Then it upgrades the quality starting from the last segment by downloading enhancement layer 6 to the enhancement layer 10 of the first segment. Our proposed method is a combination of modified AGG and HTTP2 based retransmission technique, namely H2BR. In modified AGG, the client chooses the number of layers for each segment based on the network condition, and then downloads sequentially from low to high layers of each segment. For example, the client downloads two layers, layer 1 and 2 of the first segment, and then goes to the layer 3 of the second segment. As you can see here, there may be some quality gaps in the buffer that can negatively impact on the quality of experience of users. So, to cope with this issue, we add H2BR component that was published in Package Video Workshop. It can fill quality gaps in the buffer by downloading concurrently next layers and the additional layers with priority and multiplexing features of HTTP. And in case there are some layers that cannot be downloaded on time, H2BR will terminate them with termination features. So how does H2BR work? Well, it detects the gaps in the buffer. If there is a gap, the additional layer will be one level higher. For example, in this figure, when the client wants to download the next layer 6, H2BR detects a gap at the second segment, which has only one base layer. To fill this gap, the target is to download the additional layer 7. This additional layer will be downloaded if the throughput can sustain the next layer and additional layer so that the retransmission buffer is higher than 0 and the estimated buffer is higher than a predefined threshold. In our experiments, it is the buffer size over 4. These buffers are illustrated in the bottom figure. We can see that the retransmission buffer is defined as a period from the time when the additional layer 7 is downloaded completely to the time it is played out on the screen. The estimated buffer is a period from the time when the next layer 6 arrives the client to the time it is played out on the screen. If those two buffers satisfies the conditions, H2BR will assign the priority weight for the additional layer and the next layer so that for these layers, enough throughput is allocated. Then it sends two requests from the client to the server. In the additional download process, H2BR will monitor the buffer and terminate the additional layer if the retransmission buffer is less than 100 milliseconds or the current buffer is less than the buffer size over 4. To evaluate our proposed method, we use a testbed that includes one server and one client, connected by a 4G network. For the QUIC and HTTP2, we use LS QUIC and NG HTTP2 libraries, respectively on the server and the client. The video has one base layer and 3 enhancement layers is stored at the server side. As a client, we have the ABR algorithms and the H2BR component. To shape the network, we use the DummyNet tool. In our paper, we compare 3 different methods. The modified AGG, our proposed method that is the combination of modified AGG and H2BR, and the last one is the backfilling ABR algorithm. First, we compare HTTP3 over QUIC and HTTP2 over TCP. In the left figure, when there is no packet loss, the performance of HABR over HTTP3 and HTTP2 is relatively the same. When the packet loss is more than 0%, HTTP3 provides higher average video quality. For example, if the packet loss is 1%, H2PR over HTTP3 achieves nearly 2.6 in the average video quality compared to 2.3 of H2PR over HTTP2. The right figure shows the number of downward switches, which are defined as the number of segments that have fewer layers than their previous one. We can see that when the packet loss is 0%, HTTP3 and HTTP2 experience a similar number of switches for each ABR. However, in case of packet loss, the client implementing modified HGG or H2BR suffers from fewer switches when HTTP3 is used. Meanwhile, backfilling over HTTP3 results in more switches than backfilling over HTTP2. This figure shows that HTTP3 supports H2BR to download more additional layers than HTTP2. With HTTP3, H2BR can fetch from 6 to 50% more additional layers that can significantly improve the video quality and result in a smoother adaptation behavior. Here we compare our proposed method with others. Our proposed approach achieves the best performance when HTTP3 over QUIC is used for streaming and the buffer is at least 10 seconds. H2BR achieves the highest average video quality as shown in the left figure and the lowest number of switches as illustrated in the right figure. Although backfilling provides a relatively high average video quality, it suffers from the highest number of switches. When the buffer is small, for example, just 5 seconds, H2BR cannot outperform the backfilling method in terms of the average video quality, as there is less time to download additional layers. However, H2BR provides significantly fewer switches, that is 10 switches compared to 50 switches of backfilling and 17 switches of modified HGG when using the HTTP3. These figures show that with a small buffer, the ABR can lead to buffer starvation. Although H2BR results in more storage and storage duration than the modified HGG, it's still less than that of backfilling ABR. Finally, this paper concludes that QUIC can well support concurrent streams to provide a better performance in case of packet loss. The proposed method makes non-trivial improvement in scalable video streaming, and H2PR might be abundant. That can lead to buffer starvation when the buffer size is small. Therefore, in the future work, we would like to investigate the parameter selections for H2PR and consider different network traces and the video contents to have a more general results. And that's my own presentation. Thank you for your listening. If you have any comments or questions, please feel free to ask.